basically, what we have to do is that to calculate this partition function for a given Ising system, we have to calculate this. And I will just explicitly write down to see how complicated it can be. So this energy term is, of course, minus H minus. And so if we explicitly write down this, we have plus beta H, this one. We can, because this is a plus term or additional term in the exponential function, we can split this like this as well. Maybe still it looks not quite difficult, but please remember that now we have to do this. S1 can be plus 1 or minus, and Sn can be plus 1 or minus 1. And we have this. I will just write down this. In the most. So it's basically S1 plus S2 plus Sn and beta J. And here, the non-trivial thing is it's not just a globally connected part. This one can be some very complicated form. So for example, S1, S2 plus S1, S100 and S2, S4 plus all kind of a S7, Sn or something like that. So we have to calculate this. That is the problem. That is why we cannot just solve it here and end the semester, because this is just too complicated. It is too complicated, and frankly speaking, except for very few simplest cases, it's impossible to calculate this exactly. So that is the only that's why the physicists are really working hard to apply some. First, they actually want to clarify which part is actually calculable and which part is not exactly calculable. So we have to rely on the approximation, etc. That is the thing. So this quite ugly reality is something we have to solve. So for exercise, the first exercise is systems of actually non-interacting spins. And in fact, this non-interacting spin is actually described by paramagnetism. And very nice properties. This is exactly solvable, well, easily, I would say. And partition function. Now let's explicitly write that this partition function is a function of temperature and the external field. And the starting point looks quite simple. Exponential. Of course, this collective summation is actually complicated by the fact that it includes all the different combination of the spin, the individual spin. So explicit step by step. First, this energetic term is now minus h times the sum of the spin. So it becomes beta h and sum of spin. And here, I will go through every step because this is the first calculation about this kind. So here, if we this exponential term, this is essentially simply the simple summation from S1 to Sn. But because each of the summation term is inside this exponential function, we can actually make this we can actually make this whole exponential factor as exponential beta h s1 times exponential beta h s2 times. So the summation become product thanks to the nice property of the exponential function. This is essentially nothing complicated. Essentially, this very basic identity we learned from high school. So let's write down that as exponential beta hs1 times exponential beta hs2, etc., and exponential beta hsn. And this part, splitting this as such is very essential to solve this to make this calculation possible actually. Let's imagine for a second that we cannot actually ignore this part. Then it's really almost impossible to decompose this product term like in this manner. But because this is a simple summation or linear summation, it's possible to split all the exponential factor like this. And now let's make this summation term explicit by considering, so this is actually S1 plus minus 1, S2, and etc., and Sn plus minus 1. And also, I'll just copy and paste this. They update this app with this symbol, which I really don't like. Yeah, this one. Maybe it still looks quite complicated. But in fact, you can actually use the fact that this factor is nothing to do with the other summation other than S1 itself. And this factor is nothing to do with the other spin other than this spin itself. So you can actually change the order of summation by just taking this one first and taking this one second, etc., and put them all together. Maybe it doesn't really ring a bell, so I will just talk about very simple example. So let's suppose we calculate this situation. S1 plus 1, S2 plus 2, I know, plus 1. And suppose we have some kind of function called f S1, f S2. Then let's just calculate this. So we have to consider all the possible combinations. There are 4 configurations, of course. So f S1 1 times this one, and minus 1 plus S1 minus 1, S2 plus 1 plus S this one. If you compare this result with this result, if we split this product like this, it means that the first summation is of course S1 plus minus and this is basically the form like A plus B times C plus D. So it's plus yeah, I think you know what I mean now. So this one and this one is of course identical. So we can actually replacing this kind of summation with this splitting. So considering all the possible configuration, it's the same as the product of each cases as exemplified like this. So I will just enclose this part. So part of it's kind of nice technique to remember. Yeah, this could be very useful because it's not really that intuitive, at least for me, just changing this order here. But as exemplified this, we can just switch this summation because they are all independent to each other. If there's some kind of a non-trivial part, like suppose this function is not just a function of S1, but S1 and S2, we cannot just split this like this. But because we have this all the separated term, we can now switch this. We can switch this one. So this was partition function. And we can replace this one as exponential data and etc. Product of all the way up to Sn. Then the first thing you have to realize is that for each of these n factors, this S1 or S2 or Si in general are just a summation dummy variable, what we call in the mathematical physics. It's all just the summation index. The first term is, of course, now we can actually explicitly write down the part. So it's a summation of the S1 equal to +1 case and the S1 equal to -1 case. So this is essentially exponential minus beta h. What about the next term? It's the same, right? All the way, they are all same. So it's simply just 2 to the nth power. So you already solved this problem by considering this, by using this mathematical technique. And there is actually a simpler way to express this exponential x plus exponential minus x. Anyone? Yeah, hyperbolic cosine, but you have to be careful that it's actually twice the hyperbolic cosine. And we have this vector. So since we already solved almost everything about the non-iterating spin or paramagnetic system, because we already calculate the partition function. So because partition function is like this, the free energy is minus kBt log of partition function. So it's minus kBt log of twice the, and because of the property of the logarithmic function, we can put this n in front of this log vector. So this is minus n kBt log of twice the hyperbolic cosine function of this one. And of course, the free energy per spin is F over n, so it's minus kBt log the same vector. Yeah. Let's start to calculate some physical quantity of our interest. The first one is, of course, the average magnetization. Per spin. This one is important because, frankly speaking, I mean, even if we can see the free energy landscape about this one, I mean, free energy doesn't really ring a bell in our brain. I mean, because we don't really have an intuitive idea about this, what this free energy means. So this average magnetization, in contrast, is really intuitive. It's just literally just the average direction of the spin. So it's really something we can connect intuitively. So this average magnetization, as the table in the textbook suggests, we can just take a derivative of this free energy term. And luckily, for this function is not quite simple, but when it comes to taking derivative with respect to h, the only h in this function is here. So it's not that difficult. So if we take a partial derivative there, it means that we have minus sign here, so we can just put this plus sign. And let's take a derivative in this composite function. So it's something in the logarithmic function, so it's in denominator first. And then as a chain rule, with the as a result of chain rule, we have to take a derivative of this twice the cosine hyperbolic function. So twice the derivative of cosine hyperbolic function. Anyone remember? Yeah, hyperbolic sine. So it's hyperbolic sine beta h. And we should not forget that we take a derivative with respect to h. So there's an extra beta factor here. Yeah. And we can get rid of this one. But actually, this one is 1 over kbt. So this one just vanishes. Everything is vanished except for the hyperbolic sine divided by the hyperbolic cosine. Anyone remember what this hyperbolic sine divided by hyperbolic cosine? Yeah, it's a tangent hyperbolic. So somehow we got this very nice simple result. Let's just put this as a h over kbt. Yeah. This hyperbolic tangent function appear a lot, especially some other discipline like a machine learning or any activation function or whatever. So it's really useful to learn about this function's property. And so this hyperbolic function, we can actually, let's just draw this function. So first, let's consider this function as a hyperbolic tangent function, tangent as a function of h, the external field. So what is the functional form of the hyperbolic tangent x if you do this? Is the asymptotic lines are from -1 to +1. And this hyperbolic tangent function looks like this. Very similar to something called the sigmoid function in machine learning field. So same. The magnetization is somewhere between plus and -1, and which is obvious because this one is some average value of the individual magnetization. So individual spin is +1 or -1. So the average should be somewhere between -1 and +1. And of course, we have this. I'm really bad at. I try my best, but it's not quite clean. But yeah. So of course, because of the property of this hyperbolic tangent function, it has to go through this origin point. And this is very intuitive if you think about it. If h goes to infinity, which means that the external field is very, very strong, then m should goes to +1. Just like we already checked, like this. If h goes to negative infinity, then m should goes to -1. Because both should point the same direction. And if when h is 0, then m should be 0. Partly because of the symmetry here. if H is 0, the system become completely symmetric. It's a so-called up-down symmetry. It's a real legitimate terminology. There is an up-down symmetry. And this one is obviously from this functional form of the tangent hyperbolic. Then what about the role of the temperature here? Well, this temperature is divided inside the hyperbolic tangent function. Suppose this temperature is very low, then the same change in H correspond to very large deviation inside of the tangent hyperbolic, which means that even if this very small change in H correspond to very large change in the argument of the tangent hyperbolic. So essentially, it will become like this. Because this very small change in H caused a large change in the hyperbolic tangent function itself. And the opposite case would be if T is very large, then even if we change H a lot, it doesn't change much in the space of the hyperbolic tangent. So in that case, this one should be very, goes like this. So this is this corresponds to low temperature limit, and this one is a high temperature limit. So the response to the external field when it comes to the average magnetization really depending on the temperature here. And one nice thing, or one thing to consider here, is that suppose we take this limit. Then no, let's first consider this zero temperature limit. Then what's happening here? Can you guess the limiting form of the tangent hyperbolic? It's a denominator becomes 0. So it's essentially become infinity for an ordinary value of H or any small value of H. Well, it depending on how the order of the limit, the taking limitation limit. But you have to be careful about this sign of H here. So temperature cannot be negative. So temperature is always positive. And this is a positive constant. So if H is positive, then it goes to plus infinity. So it goes to plus 1 for H is equal to positive. But if H is negative, then it goes to tangent hyperbolic of the minus infinity. So it goes to negative 1 for H 0. But even in this case, if H is exactly 0, then it can be 0 because this is a limit and this is exact. So it only takes 3 values. Any positive magnetic any positive external magnetic field, it just goes to 1. 1 means that to make every 1, it means that every spin should be in the same direction, the same for this one. So in this limiting case, let's put this as this limiting case. It's 0.0 here, but for any positive h, the tangent hyperbolic is +1. So it just suddenly jump from here to here and goes like this. And jump from here to here and goes like this. So this almost like a step function describe the behavior of the zero temperature behavior. Still, you please remember that we are not dealing with the Ising model itself. This is not even an Ising model, the paramagnetic system. But even in this case, when we consider this low temperature limit or zero temperature limit, we can have this kind of singular behavior. But again, I have to emphasize that there's nothing wrong with the strange thing going on in this zero temperature limit. So it depending on the context, but we don't usually call it as a phase transition. Still, this is certainly a singular behavior, but because we put this variable as a singular point. So this kind of behavior is precisely described in this nice figure in the textbook. And of course, we can have this very nice three-dimensional surface for this one as well, but this is not really visible. But if you saw this plot, it's just a slice like this. So this zero temperature case would be like this. So this kind of a behavior correspond to this step function behavior. But for any non-zero temperature, the function is actually smooth like this. So it goes like this. So yeah, I put every so step function in the limit, and for any finite temperature, the h this should go through the origin here, and it means that there is no spontaneous magnetization without any external field, which is quite natural. Well, you can imagine like you can have a question like well, how is it possible to have a non-zero magnetization even in the case of the external without any external field? Well, that's possible when you start to consider this the interacting spin, the J term. We'll see that part later. But in this case, quite naturally, we don't have any magnetization in the absence of the external field. And the next thermodynamic quantity is, of course, this susceptibility, which is essentially the response of this external field, response of this magnetization with respect to the change of the external field. Then we have to take a derivative of hyperbolic tangent beta h. The fixing temperature, you always remember that this beta is not just beta, it's 1 over kVt. So this fixing temperature means that considering this beta as a constant, then you have to take a derivative of tangent hyperbolic, which is according to the table, we can actually check that this is a hyperbolic second, which is a reciprocal of the hyperbolic cosine. And the functional form of this look like this. And you can take some derivative. You can take some Taylor series expansion to see the approximated behavior for a low temperature limit or high temperature limit. So in this case, even if this functional form itself is quite complicated, hyperbolic second squared, if you take a Taylor series expansion, we have this relation. And so basically, the fact that this one has this functional form is not surprising because it's basically just the derivative of this function. So as t become larger and larger, it means that the slope become narrow, the shallow and shallow. So it's just like this. The singularity, of course, happen in zero temperature. So in zero temperature, you have this step structure. So the slope is 0 here and 0 here and infinity here. That's precisely happening in this zero temperature limit. This is not just a vertical line. This actually describes the susceptibility function of this one. If we call this as a function, this is not mathematical. In mathematical sense, this is not a function, which is called the Direct delta function. Yeah. And we already derived this so-called fluctuation distribution theorem, or this relationship. Susceptibility is actually proportional to the relative fluctuation or variance in average magnetization. So if we put this function, we can have this relation, which means that this relative fluctuation of the magnetization, the standard deviation divided by the average, is actually given like this. So for a given temperature and external field, system becomes larger and larger with the larger value of n. We have very sharp distribution because the relative fluctuation becomes smaller and smaller with this proportionality. So if we quote this textbook, which means that the distribution of total magnetization become more and more sharply peaked around the average value with increasing system size. And that is the standard behavior of the system of non-interacting spin.